everyone. My name is Nabila, and I'm the Graph Neural Network stream owner here at ACE. For those of you that are new, ACE is a global community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We're currently working on creating a repo of authors talking about their research because with all the new papers coming out every day, it's really hard to figure out what to pay attention to. So our hope is to make that process just a little bit easier by highlighting papers through our spotlights that we think would be of interest to the broader community. We host free live sessions like this 3 to 5 times a week, and we also produce premium content delivered in workshop format. We're actually running a Graph Neural Networks workshop right now. If anybody's interested to go check it out, you can head on over to our website, ai.science, for more information. So today we're actually joined by Faraz Zaidi, who is an advisor in the health analytics team at the region of Peel. And in his role, he develops data-driven solutions using advanced analytics, complex algorithms, and visualizations to solve health-related business problems. His research interests lie in network science, social network analysis, graph algorithms, and visualization methods. He has a PhD in data mining and visual analytics, an MBA in management, a master's in complexity and algorithms, and a master's in software engineering. Faraz is more than qualified to lead this stream. For those of you that follow this stream, we typically covered graph neural network style papers. Faraz is actually going to cover some of the more traditional network analysis, social network kind of papers that you'll typically find in this space. And so we're super excited to have you, Faraz. So the floor is yours. Go ahead.
Thank you, Nabila. It's a pleasure to be here talking about this. Okay, so getting started. So my topic today is about identifying influential nodes in complex networks. The structure of the talk is pretty much classical. I'm going to introduce the problem, give you some background. I'm going to talk about methods and algorithms, have some discussion points, and then I'm going to conclude my talk. Okay, let's dive into it. So just to set some context, social connections can be modeled as a network or a graph. For those of you who are not aware of it, nodes and edges or vertices, as we call them, they can be used to model any social network, a network of people where individuals are represented by nodes and the connections are represented by edges. Just a word on, there are several theories that explain why our society is structured this way, like there are theories in homophily, extroversion, and social ties. I'm not going to go into that. What I'm going to start off with is we have a social network and how can we actually identify influential nodes in such a network. Now, it is important to understand that the position of an individual in a graph or a network is important. And that is, in some terminologies, called kind of like the influence of that individual in the network. There are other terminologies that that refer to the same concept, such as centrality, hubs, critical nodes, powerful nodes. Depending on the domain, people have used and introduced different terminologies for the same concept. For this talk, we are just going to talk about influential nodes or influential individuals. Okay. So in the current context, this has become very important, influential nodes and COVID-19 spread. So just consider this example, the graph that you can see here on the slide, the node I, which is somewhat central to this network. Assuming that that person gets COVID, it can easily transmit COVID to the entire network simply because its position in the network. What we are trying to do with this problem is trying to identify or assign a quantitative measure to this node and in fact to all the nodes in the network to estimate what the influence or what the impact of the nodes are with respect to their position in the network. Ideal case would be if we are able to identify the influential nodes in a network, we should ideally isolate them, quarantine them so that they can stop the spread of the virus or any other contagious disease in the network. So the same idea of influential nodes can be applied in many different applications. It has probably one of the largest applications in networks and graphs. One of the biggest applications is in target marketing. So for example, let's say if you're looking to buy a mobile phone. So what you would do is you're going to ask your friends about their opinion of which mobile phone you should buy, which model, which brand. The people who are able to actually influence your buying decision would be represented by the influential nodes in such a network. Now, again, this is just an example from marketing where you are trying to sell a product, but it could be anything. It could be opinions, ideas, information. Like in the current context, we have the election, US election going on. So if an individual person is able to influence other people to vote to a particular party or to a particular candidate, that would again qualify as an influential node or influential individual in a social network. Another application is in infrastructure networks. So for example, here you see power lines. So, the power lines are distributed all over the country, across countries as well in continents. What are the critical infrastructure points that if for some reason fail or stop working, the entire infrastructure of that power lines would actually stop working, and there would be a blackout. And this has happened in the past, and that's why it makes this kind of like study very important. Another application here you see on the world map is the direct flights around the world. So it could be shipping paths as well, where people are exporting goods. It could be flights that carry passengers. Again, identifying influential nodes would be a good idea to identify the robustness, to study the robustness of such a network, and basically estimate what are the critical nodes or what are the influential nodes that can impact greatly the entire network. Okay, formally in mathematics and statistics, we call this percolation theory, which is basically the study of a network or a graph where when nodes or links are removed. So for example, in this graph that you can see now, if I remove the central node, which is node I, it will break the entire network into smaller pieces. And here you can see that if, assuming that these are people and we are talking about the COVID-19 spread, if people are not directly communicating to each other or coming in close contact, the spread of virus would stop and would actually be localized in a very small piece of network. So that's what we are trying to do. We are trying to identify the influential nodes and see if there's a way we can identify them. We can ideally quarantine or isolate them and stop the spread of the virus. So formally, given a network G with an N nodes and E edges, we want to determine a ranking of nodes to identify influential nodes. For this talk, I've limited myself to simple and undirected graphs, but the study can very well be extended to multi-graphs and directed graphs. So looking at the literature, there are like hundreds of methods to actually do this type of work. And every time a new method comes in, it kind of like tries to prove that the new method is better than the previous ones. So what I've done is I've looked at the literature and kind of like classified it into three categories. The first one is topological measures, which basically take the entire topology or entire connections and the entire structure of the network. The second one is the process-based networks, which is basically we run some sort of a process and we can identify influential nodes through that process. And the third one is basically a kind of like a more wider, broader category where we use heuristic methods that work well, obviously, but not necessarily always get the best results. Okay, so here are some of the techniques that I've picked up for this talk. So I am going to go over all of these, but just to highlight the fact that this is not an exhaustive literature review. These are some of the most famous ones or the ones that have performed consistently well in different types of networks, but there are many, many others. Okay, so the first one is very basic and the very famous one. It's called degree centrality. Most of the people who have studied graph theory in one form or the other must have gone through this. Basically, it's the number of connections of a node. So you simply count the number of connections of a node, and the node with the highest number of connections is deemed as the most influential in the network, and you can use this idea to carry on. A simple variation on this degree centrality is the iterative or adaptive version of it, as it is called in different literature. What it does is basically it calculates the degree of all the nodes, identify the highest node with the most number of connections, removes it from the network, which basically changes the entire structure of the network, recalculates the degree, and pick the highest degree node now in the changed structure. So this is why we call it iterative or adaptive. We have to recalculate the degree every time we identify the most influential node, remove it, and keep track of the nodes that are removed in the order they are. So that gives us the ranking. Another famous and basic algorithm and technique again dates back late 1980s or late 1970s actually, is between a centrality. So the idea of between a centrality is basically you calculate shortest paths between all pairs of nodes in a network. Once you have calculated those shortest paths, the influence or the importance of a node would be calculated by the number of shortest paths that go through it. So intuitively, if you look at this graph and look at the black node in the center, so all the nodes that are on the left side of this for the shortest path would actually go through that black node to reach to the nodes on the right. And similarly, when you calculate the shortest paths for the nodes that are on the right and going to the left nodes, so this would mean that the node that which is central in this graph would have the highest between a centrality. So again, there's an iterative version or adaptive version of it, which has in some cases performed better than the classical between a centrality. Okay, another famous one which has attracted a lot of interest in many different fields, specifically biological studies and protein interaction networks and so on, is causal decomposition. So the idea of this algorithm is consider this graph and consider the degree of a node A, which is 1. It has only one connection. So what we do is we iteratively calculate the shell of, we assign a shell number which goes from 1 to n to all the nodes. So in this case, the way we calculate the shell for A is 1, since it has degree 1. Then what we do is we remove all the nodes that have degree 1 from this graph. In this case, we'll remove the node A. If we remove the node A, the degree of B will now become 1. So that will also become part of shell 1. And we repeatedly do this until we have no other nodes that have degree 1. Once we have identified all the nodes with that belong to shell 1, we move on to shell 2 and shell 3 and keep going on until we have assigned a shell number to all the nodes. The nodes that are have the highest shell are the most influential one. So PageRank. So this is the famous PageRank upon which Google is based. So for this example, just for the explanation purposes, I've just used a directed graph, but the same method can be used to calculate PageRank for undirected graphs as well. So what PageRank does is it's a process-based method. So in this graph, we can see 4 nodes, A, B, C, and D. So initially, an equal weight or equal importance is assigned to all the nodes. So in this case, we have 4 nodes. So we just divide 1 with 4 and get an equal importance for all the nodes. Now, let's just, for the sake of example, we're going to calculate the next iteration and calculate the weight for, or the importance for D. So if you look at D, it has one incoming edge from B and one incoming edge from C. So what this method does is it uses the importance of the neighborhood of D to calculate the importance of D. So the neighborhood of D is defined as the incoming edges of D, which in this case are B and C. So the current importance, which was initially assigned to B, was 1/4. And similarly, the same importance was assigned to C, which is 1/4. Now, since only there's one outgoing edge in B, and that goes to D, so B assigns all of its importance, which is 1/4, to D. For the case of C, it has 2 other outgoing edges apart from one that is going to D. So C has a connection to A, C has a connection to B, and C has a connection to D. So its importance would be equally divided among three nodes, which is A, B, and D. So its importance would be 1 upon 4 divided by 3. So the weight that it's going to give, the weight that's going to come from C, or the importance that's going to come from C to D, would be 1 upon 4 divided by 3. And the weight that's going to come from B to D would be 1 upon 4. And we simply add these two weights or importances to get a new value of D. We similarly iterate over all other nodes and calculate a new weight for all the nodes in iteration 1. And then we keep on repeating these iterations until these weights stabilize, or to a certain number of iterations that we prefer to. So that's how we actually calculate the basic PageRank algorithm. Just to let you know, Google currently uses different variations and versions of PageRank. So this is just the classical algorithm that I've explained in this talk.
Faraz, just a quick
So
question for you, if you don't
yeah,
mind. On
yeah,
this
go ahead.
classical one, is there a concept of neighborhoods, like go branch out one more than just the first hop?
So can you repeat the question? I'm not sure if I understand that.
Yeah, no worries. So when you said the calculation for D, you said, oh, we look at the importance based on based on its
The
neighbors, B
neighbors?
and C. And if
Yeah,
B and C are connected to other things, then their importance towards D changes. So do they ever go
exactly.
more than just the one hop in the most, like I guess the most basic is one hop, but is it common to
So,
do more
yeah.
neighborhoods?
So to be honest, I'm not aware of it. I'm only aware of this classical version. I know that they use a damping factor to
Oh,
take
okay.
care of the random hops, but I'm not sure if PageRank does more than one. There is another algorithm I'm gonna talk about, and that actually increases the neighborhood. It's
Okay,
very
gotcha.
similar to PageRank.
Cool, thanks.
Okay, so community-based attacks. So the next method is again a process-based method. So what it does is it runs a community detection algorithm or clustering algorithm on networks, identifies communities. So if you look at this graph, you can clearly see that there are like 4 different communities that are centered around I. What it does is once it has identified communities or clusters in a network, the nodes that are intercluster or connect different clusters are taken out as important nodes and assigned a high influential score. Once all those intercluster nodes are removed, the degree of a node is used within the cluster to estimate the importance of that node. So that's how it works. So you identify clusters, you identify the nodes that are connecting different clusters, you take them out, rank them as highly important, and then within the community, you just take the degree of the nodes that are inside a cluster or community, and assign a ranking based on degree. Random box. So there are different methods based on random box. So the one that I've used is a very basic one, a classical one again. So what it does is takes a radius, predefined value of radius r. For every node, it does a random walk for radius r or n steps. And every time it visits a node, it increases its counter to 1. Once we have done this iterative process over all the nodes that are most visited are deemed as the most influential one in this network. The good thing about this network is you can basically run it for small values of R, relatively small values of R than the size of the network, which basically increases the time complexity, and the algorithm can be more efficient as opposed to being slow. So now moving on to the heuristic-based algorithms, this is the WL algorithm. So what it does is it somewhat answers your question of the one that you asked about PageRank. So what WL algorithm does is it uses the immediate neighborhood at distance 1, but a general form of this algorithm is this collective influence that I'm going to talk about next. So in this case, what we do is the influence of a node I is calculated based on the degree of the node I multiplied by the degree of the node of all the nodes that are in its neighborhood. So in this case, we are calculating a degree of node I. So Ki is the degree of node I, and Kj is the degree of node J, and J has all the nodes that are in the neighborhood of I at distance 1. If we generalize this idea, it becomes a collective influence. So what it does is it takes S parameter, the radius. In this case, the radius is represented by L. And the example that you see in this image is to calculate the collective influence of node I here in the center. We have used a distance radius of 3. So all the nodes that have a degree that are at distance 3 from this node I, the degree of these nodes is summed up to calculate or estimate the influence of node I. Okay, so that kind of like wraps up a quick summary of the different techniques. Nabila, any questions before I move on to the discussion points?
No, not at the moment. Those were very clear. Thank you.
Good. Okay, so for those of you who are into the theoretical aspects, this is the identification of influential nodes is basically an NP-hard problem. So there is no known linear time algorithm that can solve this problem. Now you can very well imagine that with this kind of like this type of well, we have lots of networks, like we've got LinkedIn, Facebook, Twitter. So these nodes have like millions and billions of nodes. So it is important to understand what their topological structure is. And since it is an NP-hard problem, we do not have any linear time algorithm. So any algorithm that tries to solve this problem runs into the problem of efficiency and solving the problem in quick time. So that's one of the problems that we can think of simply because of the fact that this is a complex problem for large networks. The other point that I would like to make, and that has come out of my personal research, is that the topological structure of these different networks, the ones that I've shown you, like the infrastructure networks, the road networks, the power line networks, the social networks, and then the virtual, like the online social networks such as Facebook and LinkedIn, the topological structure changes, or the structure of the graph changes to a large extent. So there are different dynamics that actually result in the formation of these networks. So since the underlying structure is different, the different methods result in different influential nodes. And some methods actually perform better on certain type of networks. And I don't want to go into the classification of networks, but they're like small world networks, scale-free networks. And then within those small world and scale-free networks, there are further classifications. But the idea is that since the topological structure of these graphs and networks changed largely, different methods perform and give different results for these methods. One of the things that that has come out recently, so the 3 papers that I've actually used to prepare this talk, they kind of like are contradictory to each other. So one method proves that collective influence is better. One method proves that another method is better. So there is no consensus, or there is no standard method that can be generically applied to all different types of networks or different topological structures and get the best results. So this makes this problem kind of like an open-ended problem, and researchers are currently still working on this problem. Within the current context of COVID-19, this has become further important. So I've mentioned a little bit about large networks. So most of the methods, one of the problems with topological methods and the process-based methods is that for large networks with millions of nodes and billions of edges, they're slow. Any algorithm that requires iteration or repetition would require more than linear time in terms of number of nodes, and that would make the algorithm slow. So here are 3 solutions that I propose about this problem. So one, which obviously the most straightforward and what Google uses to implement its PageRank versions, is using parallel and distributed algorithms. Another approach that I'm currently exploring and working on this is using machine learning methods to capture topological features of a graph. And once we have those topological features, apply a machine learning model to identify the inferential nodes. So to the best of my knowledge, I haven't seen any work in identification of inferential nodes, a more supervised learning approach, and that's what we are trying to do. And the preliminary results that we've found are very encouraging, and we hope to publish them soon. Another approach that I would like to test out, and we haven't done much work on it, and I haven't seen any other work in the literature, is using graph reduction methods, which is like converting graphs to tree structures or quasi trees, which would significantly improve the number of edges in a graph. Once the number of edges become in the order of number of nodes, so if you have a tree, you would have exactly n minus 1 edges, where n is the number of nodes. If you have a quasi tree, let's say you have for every node you have approximately like 2 edges, that would be like approximately 2n edges in the graph, which still is a very low number as compared to the number of edges that we commonly see in large networks or very large networks. So this makes kind of like these two avenues, like exploring machine learning algorithms and exploring reduction methods, very interesting to explore this problem further. So these are the 3 papers that I just mentioned. So fairly recent. One of them is from 2020. The other 2 are from 2018. So I will highly recommend that you check these out. So there are a number of other methods that are listed in these papers, and this is fairly active. Like I said, in the current context of COVID-19, and it would be really interesting to see how people use these techniques to solve like such as COVID-19. I would like to thank you all, and I would be happy to answer any questions. Over to you, Nabila.
Thanks, Faraz. That was a good intro. We cover a lot of GNN stuff, but we always forget about the basics, like the purely statistical methods that even Google uses that we never cover. So thanks for that. I wanted to ask you, that 2020 paper, is that collective influence?
No, collective influence is actually from 2015. It was published in Nature. So it was from the same people that which have published this third one, which is Moron and Maxey. Actually, I had the privilege of working with that team, and I actually contributed to that paper by helping them implement that. It was back in 2015 or 2014, in fact, when I was doing a postdoc with Professor Maxey there in that team.
Oh, very cool. I thought it was interesting because usually these statistical methods are very old school and grounded in theory that they've just been applied in the newer years. So which was the 2020 algorithm?
So the 2020 algorithm is based on I haven't discussed this method in this talk, but I can give you a quick overview. It's basically about I think it's called DWT. So it uses a local measure which is based on structural holes. And what the idea is any algorithm that would run for the entire graph would be slow. So what they do is they try to exploit the local network structure and identify structural holes, and based on that, they identify the inferential nodes within a local network, and that's how they build on the ranking system.
Okay, is that how they get away from the scale problem? Because if they have a giant network, they cut it up into smaller
Exactly.
sections. Okay.
Exactly. So they just again, that doesn't guarantee that it will give you an optimal solution for the global network, but the results actually are better than. So here's the tricky part, right? So they've used, I think, if I remember correctly, they've used 6 or 8 networks, real-world networks, and they've shown that their results are better than the collective influence CI and degree centrality and betweenness. But I highly suspect those results, not because that I'm doubting the paper. It's just that the networks that they have used, that method actually worked. I'm sure that I can produce a network that their method was going to fail and some other method would actually perform well. On that same line, I mean, in many of the networks that I've seen, degree centrality, and the classical degree centrality actually outperforms many other algorithms. So you don't even need to worry about like difficult algorithms. It's just that there's a lot of variation in the structure of networks. Networks emerge from biological networks, network emerge from infrastructure networks, social networks. I mean, you can create a network from almost anything. So the idea is degree centrality doesn't work all the time, but in many cases it actually works.
Okay, interesting. Actually, on the idea of motivating these works, Parham has a question about where was it? Oh, I lost it. Oh, the hypothesis of the WL algorithm. So you said it was like they take the degree of the current node and they multiply it by all of the degrees of their neighboring nodes. But
Yeah. So.
what are they hoping to
Mhm.
achieve by doing that?
So it's very intuitive actually. So the importance of a node is is determined by the importance of its neighbors. So if you look at it this way, I mean, for example, let's I use this example often. So let's say the president of United States, he's a very influential person.
Oh,
The
that's why you were
current president,
smiling.
yeah. So Trump, I use this example a lot. So Donald Trump is very influential, right? And then there's Bill Gates, who is very influential in the technological world, and then there's Elon Musk, who is influential in his own realm, right, in his own world. Now, if a person who knows all these three people, his influence would be higher than the three in their individual influences, like political influence from Donald Trump, technological influence from Bill Gates, and then Elon Musk's like innovation engineering. So if someone who knows all these three people, his influence would be higher. So that's the idea of the WL algorithm. You not only consider the number of connections of an individual, but the importance of its neighbors as well. And it's very intuitive, very similar to PageRank. This is just that they use different calculation methods.
Okay. I've played around
And
with some of these. Oh, I'm sorry, I cut you
mhm.
off. Go ahead.
No, I was just going to say that collective influence is also based on the same idea. It's just that it generalizes. It doesn't just talk about the immediate neighbors, but it uses a parameter which you can increase the radius or the distance of your neighborhood.
Okay. Actually, that's kind of what I was going to ask because a lot of the centrality algorithms are solely based on position in the graph. And because there's no other
Mhm.
information, like what is the differentiation factor between a lot of them? You said degree centrality, which is the most simplistic version of this method, is like can solve most problems. So why go for all these different variations? Like unless there's some extra piece of information that is key that you would learn.
Yeah, so the key is hidden in the structure itself, the topology itself. So so for example, again, the simple example is the power of these networks is in the connectivity, right?
Mm-hmm.
So let me show you an example. It's easier to explain through that. Mm, So you see in this one, you can see the black node is kind of like central, right? So
Mm-hmm.
the position of this black node is central, but the position of this node is of being central is determined by the position of all other nodes. So the differentiating factor is not the information, which is just the number of connections of this node. It has just 5 connections, but the overall structure and its position within that structure, and that changes a lot. So if all these different methods, so for example, in this case, I mean, let me go to a simpler case. In this case, like the central node has degree 4. All other like degree, the node A has degree 3, which is not much different from node I, but the position of I is very important. So in some cases, there's only one central node and could be connecting like two big hubs, for example. So it becomes central just simply because it's connected to two hubs, and it becomes important because of that. So the position of the node is important, which can only be captured if you like calculate a kind of like a metric which kind of like captures the overall structure of the network, which is practically impossible because for millions of nodes, it's difficult to calculate.
Okay, so what you're saying is the position informs on different, like in itself in different measures. Like this between a centrality would pick this out, but degree
Yeah,
centrality not necessarily because A would be very
exactly.
close to I in some sense because
Ex-
it's 2
e-
versus 4.
exactly. And then you can look at different examples. Those are like two classical examples, simple examples. But for a network like this, I mean, it's difficult to pick it up.
Okay. There's obviously a lot of ML folk that follow this channel, so Parham's next question is a fun one. How do you validate these centrality measures? Because there's no ground truth, right?
Yeah, so that's a really good question. So I didn't go into that as well. So so again, it depends on the domains, right? So I can mention one simple, the most simplest method is called measuring robustness. So what you do is once you have the ranking, what you do is you start removing nodes based on the ranking. So you remove the most influential node. Once you remove the most influential node, one node, you calculate the biggest connected component, which is left after that removal. Then you remove the second most influential node. Then you look at the impact that it has created on the remaining network, and then you pick up the biggest connected component. So the more impact nodes removal creates, which is basically it reduces the most size of the network. Uh, that basically gives you a quantitative method. But in sociology, people don't use that method, the robustness method, which basically looks at the giant size or giant component or the biggest component, connected component. What people use, they use simulation algorithms. The two famous ones are IC and LT, independent cascade and linear threshold. So both are influenced by social context. So you know. So linear threshold, what it does is it has so for example, a central node is a neighbor of a central node exerts pressure on that node, and there's a linear threshold after which that node gets influenced. So you run simulation studies using the most influential nodes identified through one of those methods as central nodes, or already, let's say, so if for example, let's take the example of buying iPhone. So the concept of early adapters, where people adapt to a new concept.
Mhm.
So uh, with both LT and IC, independent cascade, and LT, linear threshold and independent cascade, the idea is you pick a bunch of nodes and turn them, let's say they bought iPhone. Now they will exert some sort of social influence on their neighbors, and that social influence would be triggered by a certain probability or a linear threshold, and they kind of like exert their influence on the others with a certain probability, and that probability actually converts those people uh, into buying, let's say, iPhone 11 for this example, or voting for some person, or picking a specific sport, practicing a specific sport. So those two IT and LT and IC algorithms are probabilistic methods that simulate uh, if we select this method, let's say degree centrality, what how what's the size of the network that they can actually influence using those simulation studies and different probability values. That's how they measure it.
Oh, that's interesting. I didn't realize that. But I suppose they can also, like in your example of the iPhone and stuff, they can go out and collect the data to verify this is the most influential person for iPhones, for example.
Exactly. They can do that. And in that case, I mean, that would be like that would be measured better by robustness, right? Like for example, I don't know all that when I mentioned targeted marketing, like so. For example, Nike sponsors like different sports people, so people are encouraged to buy Nike goods. So they don't need to do that. Look into their neighborhood. All they need to do is find the most influential person. Let's say I don't know. I can think of Michael Jordan or something. So people buy goods just simply because they are influenced by that most influential person.
That's interesting. That's probably how Instagram finds everybody. Um, I'm curious though. So these methods are primarily what the big tech companies use, right? Because everything is so densely connected. So then, what is the biggest challenge do you think when using these sort of methods for really large graphs? Because I can think of multiple challenges from the graph neural network side, but this
Mhm.
seems like beside your inference computation, or I guess that is your biggest one, the computation, right?
Yeah, I mean, so any method that has to visit multiple nodes for its calculation, right? So degree centrality is easy, right? You can just look at the neighborhood, smart implementation of, and an edge list would just give you, you simply traverse the list, it gives you the degree, and that's it. Now, for example, betweenness, I mean, for every pair in a graph, you need to calculate shortest path. So in order to find the shortest path, you need to run a breadth first search algorithm from one node to the other.
Yeah,
So you run breadth first search, and they are intelligent ways to do it, but still an exact calculation is like, I believe, n square. And if you run a between a centrality algorithm, it would be really slow, and n square in terms of number of nodes.
I see. Okay, so it is a scale. So in graph neural networks, it's the same problem, but we have a bigger problem there because we have to deal with the feature space as well as the as your position, I guess.
Hmm.
Um, so I'm wondering, you said that there were some COVID-19 projects related to the impact on influential nodes. Have there any that have taken off, in your opinion?
So I'm sure a lot of researchers who are working in this kind of like area are using the same idea to identify influential nodes. The only problem or the biggest challenge with this is these are all like simulation studies, right? We cannot, there's no way we can capture the real world social network. I mean, well, unless until people allow us to like the researchers to actually get access to their mobile phones, and then they can track exactly where a person is going and where he's moving around. That's the only way we can actually build a realistic network. Otherwise, all we can do is we can simulate how a real world network will look like based on cities population, for example, census data. We know that in a specific household these many people live, so they are all in a close contact, and then they probably visit the closest grocery shop, so that's where they're going to meet all the people in their neighborhood. And then their kids go to the same school as the kids in their neighborhood goes. So that's how they can actually use census data to kind of like estimate what that real world social network will look like in a city setup. But basically, to the best of my knowledge, I don't know that any real data has been collected on such a large scale.
Oh,
Currently, what we do is we just use simulation studies to generate like a synthetic population, and we test our methods and identify based on those methods.
oh, didn't realize it was such a challenge. Actually, going back to your scale question, you said tree-based methods are a good alternative to cut down on the complexity, but don't you throw away a lot of connective data that way?
So yeah, so here's the tricky part. So this is the idea actually is not novel, right? So I've read a paper
Mm,
in 2006 that what it did was identified uh, or let's say embedded the relational information in one edge. So kind of like a simplification. So the idea was, for example, one of the basic algorithms in graphs is minimum spanning tree. So that would generate a tree from a graph. Now, the way you generate your minimum spanning tree can determine which edges are selected. Once you have generated a tree, you can use a graph clustering algorithm on that algorithm. It would be really efficient simply because there are only trees now. It's only a tree. Now, with capturing the structure, if there is a way to embed that knowledge, that so for example, let me give you an example. Go back. So you see in this graph, we know the black node would be central, right? So all we need to do is remove the all other edges. So we'll still have this if we do it intelligently in such a way that we reduces this graph but still captures or maintains that this black node is still central to that tree. It still would have like a high central value. So again, to the best of my knowledge, no one has actually used graph reduction methods in such a way, like to the level that you create a tree or quasi tree, and then try to apply those methods, or try to use influence mining algorithms to identify influential nodes. So to the best of my knowledge, no one has done this, but this is again one of the things that that's on my to-do list. As soon as I get some time, I'll definitely explore this.
you've given us all your research ideas. What will you publish when ACE publishes its next?
I'll be happy to I have a long list of to do things with these. So this is just in this like influential mining like domain. I have like so many ideas. I'm not worried. I'll be happy if someone takes up my idea and tries to write a paper on it.
That would be interesting. What's the flip side of these influential nodes? Because I had somebody today that came to me with a problem about they want to model the outlier, or not the outliers, I guess the parts of the graph that are sort of missed out on so that they can identify like market capital, I guess. Because these people
Hmm.
don't interact with the rest of the node as much. So this is kind of the opposite of influence, right? Is that as studied as much?
Uh, so, uh, so again, during my PhD, I did work on this a little bit. To the best of my knowledge, I'm not aware of it. But now that you mention it, this could be like a good kind of like a problem to study where you're trying to identify not just one individual, but a group of individuals that are least influential, and they are like so. For example, in a large network, you identify influential nodes, but you're bound to miss some like local groups that you cannot influence because the influential nodes that you have selected, they are nowhere near that kind of like just an individual, because for an individual you can do the flip side, right? You've got a ranking, so you can start from the least influential node in this network, and you'll have identified an individual. But identifying such a group which is kind of like position wise distant from the highly influential nodes, yeah, definitely that would be something really interesting to do. I don't know that this has been done before.
Okay, I get we you cut out for just a little bit, but I was as you cut out, I was like, okay, what jokes will I tell? But also, if the distance between that and the influential node is high relative to everything else, I suppose you can pinpoint non-influential nodes, right?
Yeah.
That would be a third paper suggestion. Um, in a lot of the graph neural network papers, heterogeneous graphs is like the low-hanging fruit because what do I do if I have a fancy algorithm for a homogeneous graph? Now me translating this into a heterogeneous is like the low-hanging fruit. But I didn't hear you speak about different types of nodes in a graph. So what do you do there?
Yeah. So again, so there are different ways to handle those, right? So you can do like multi-graphs. So for different types of nodes, you can create different levels of network and apply these methods on those different graphs. So you literally create for one type of nodes, you create a graph, you apply the method, identify the most influential node. For another type of node, you identify that graph and you apply those methods again on that specific graph, and then you kind of like pool the results to see. You can use ensemble methods as well, like you try to like use different methods, and different methods would actually result in different influential nodes in different graphs. Again, I'm very limited on the knowledge. If ever this has been done, I'm not aware of it.
Did you say for the to compute the influence to project it to a homogeneous version?
Yeah.
Okay. I've seen that. So I've used Neo4j, which is like a graph database, and that is the backbone to all their methods. Like no matter how crazy your graph is, you have to project it into a homogeneous space before you can use it. And I was wondering if that's like a them limitation or really that there's no heterogeneous version of these algorithms.
No, I think to the best of my knowledge, I have not seen. I mean, the way people have done it is they've individually applied like on uh, the homogeneous version of it, and then just projected out the results.
Okay, interesting. So I guess I did a last call for questions to the audience, but we do cover a lot of graph neural network papers here. So like naturally, we would wonder why would anybody want to do the old statistical methods that don't encompass node features? What is the biggest selling point to be in this field now compared to how graph neural networks are taking off?
Yeah,
You can say
graph
there's
neural
nothing.
networks. No, so here's the thing. So I believe it's an evolution of the field as well, right? I mean, no one ever talked about graph neural networks before, like a couple of years ago, or even 3 years ago. Let's just say it's fairly recent. Or correct me if I'm wrong, but it's fairly recent. At least when I did my PhD, I mean, even neural networks were not that much in the market, right?
I'd say the
It
last
was
few
really.
years has really taken off, even though like the papers like Graph Sage and stuff has been dated to 2016,
Mhm.
and some other seminal works look just around that time. So relatively old, but it's recently take old in terms of ML, but uh, Like the more
Yeah,
papers have been coming out the last year or so.
yeah, I guess, I mean, once, deep learning kicked in and people started using neural networks more, I mean, they started to expand and graph neural networks became popular. I did my PhD in 2010, right? So even back then, not many people actually even used neural networks, and even graphs were a big thing back then. So yeah, so the only thing that I cannot compare because so here, let me give you an example of how this could be done. Mm, so graph neural networks bring a whole new dimension to the party. So not just feature based, but so what I've done with machine learning, what I've done is I've generated lots of graphs and I've identified not features, but their structural position as features, and then tried to apply machine learning algorithms.
Right.
And that's one of the techniques that I talked about to try to identify influential nodes. Uh, Features make data rich, right? Graph data very, very
Yeah.
rich. So that's why I say that they kind of like bring a different ball game to the party, right? It's a totally new world when you enrich your data with feature spaces. Like you're gonna have very very different features. So that doesn't replace, but that simply like augments the power of existing networks and existing like methods in the networks.
Hmm.
Does that answer your question?
It's kind of the same argument of why would you do statistical machine learning when you have deep learning? That's pretty naive because somebody will reinvent something new in statistical and they'll try to deep learn that. And it's the same in the graph space. But I was just curious about that. Parham says that GNNs versus centrality measures solve different problems, I guess, but you could also compute an embedding for a node and then see how it compares with all the other embeddings. And then you could say something different about that current embedding. So I feel like you could solve all these problems with the GNNs, but you pay the price of now having to deal with the feature space. What do you do if you don't have features, right?
Mm-hmm.
Um, it's very complex. Anyway, this was a good talk for us. Thanks so much for joining us. I think the audience has had their fill of questions. So thanks for joining us and sharing your knowledge on this work. And thanks everybody for tuning in. Slides will be posted at the event link on our website, ai.science. If you like this content, please make sure to subscribe to our channel, ML Papers Explained, to get notified about all the live sessions and all other free content that we do publish. So thanks so much, everybody. And until next time, we'll see you around.